Today we will have two presentations, 10 minutes each. The first one is from Francesco Jamal Sheiban from Politecnico di Milano. He recently graduated in bioengineering and is currently doing his research fellowship at Politecnico di Milano. In his talk, he will describe modeling and simulation of cerebellar interactions in sensory motor talks. So I give you the stage, Francesco. You can share the screen.
All right. Thank you for the kind introduction. So I guess I'm sharing the screen and everything is fine. Okay, perfect. Okay, so good afternoon, everyone. My name is Francesco Jamal Sheiban, and today I'll introduce an in-silico implementation of a reach-to-grasp behavioral task. Now, to give a bit of a context, the reach-to-grasp associative motor tasks are experiments in which animals are trained to associate a stimulus that can either be an auditory stimulus, a visual stimulus, or a somatosensory stimulus to the availability of a reward that can either be a food pellet, as shown on the left, or a water droplet, as shown on the right. These kind of tasks can be imaged with commercial cameras, such as infrared behavioral cameras, or with custom neural interfaces, such as fluorescence microscopes or electrical neural interfaces. So to study the underlying neural mechanism of the observed behavior. The objective of this work is indeed the implementation, virtual investigation of the neural mechanism imaged in vivo, and in order to adhere to the 3 R's principle for a more human and ethical research. So the idea is that a complete and full implementation of this kind of experiment in silico, so virtually, would allow to investigate this mechanism by reverse engineering some causes and some known hypotheses, as going from the descriptive level to a predictive level and replacing the need of further animal studies. For our work, we used the Neurorobotics platform. This is a software tool developed by the Human Brain Project and part of the eBrain infrastructure that allow to perform virtual experiment with simulated neural robots by letting 2 neural simulators run in parallel, one neural simulator Nest and the 3D physical simulator Gazebo. This simulator can communicate in real time with the use of custom user-defined transfer function that allow an input-output mapping between the 2 blocks. And for our specific implementation, which shows among the available robots on the platform, the ICAP humanoid robot, as it was able to perform the reaching grasping movements. We set up a minimal virtual environment composed of a resting bar with 2 floating cylinders in front of it, mirroring the in vivo water delivery needles, as well as a screen that we use to deliver the GoQ signal. And with these implementation, with the design choices, we were able to formulate some protocol phases. So the robot receives a stimulus, somatosensory stimulus on its shoulder, given by the rotating bar, that indicates which of the 2 needles will deliver the reward. So a stimulus on the right shoulder indicates that the reward will be delivered on the right needle and vice versa. After these directional stimulus, the robot has to wait for a go cue that is given by the screen turning green, so that it knows that the reward is being delivered and it can perform the reaching and grasping movement. As for the neural simulator, we combined different findings from nature, and we identified a set of areas that we distributed over 2 identical hemispheres, as shown on the right. So in particular, we identified a set of thalamic areas that engage in working memory and decision-making mechanism with cortical areas. And we identify a role of the cerebellum in learning the association between the go cue and the reward stimulus upon successful trials, so that it can influence the thalamocortical ongoing dynamics and drive the subject to execute the reaching and grasping movement, so to issue a motor command. With these 2 components designed and implemented, we carry out initial tests to validate the input-output mapping of our transfer function. So we embedded the post-learning neural dynamics in our neural network model, so that we were able to monitor the correct flow of information in this visual environment with a spiking with a raster plot of the activity in real time. And indeed, we saw that we were able to monitor the correct touch of the robot on the resting bar. And here is the pseudocode of a transfer function by looking at the contact point list that are the names of the object that are touching, that are in contact with each other in each frame given by the gazebo engine. And we, once both the left hand and the right hand were in this contact list, then we set the resting bar contact equal to true. So the robot was actually touching the resting bar and waiting for its turn. We then used a similar approach to deliver the stimulus to the right hemisphere when the right shoulder was in this contact point list. So some object was touching the robot's shoulder. And once detected this contact, we set the somatosensory stimulus neuron firing rate greater than 0 only on the right hemisphere. So we delivered the stimulus to the right hemisphere of the neural network model. Similarly, we set the firing rate of the Goku neuron greater than 0 once the cameras from the robot eyes detected a quantity of green pixel greater than a threshold. So the screen turned green. And combining these two approaches gave us a way to selectively deliver the reward only when a correct trial was completed. So if the robot was sensing a blue object on its right field of view, and if the right hand was touching the right needle, so if this pair of contact names was in the list, we set the reward stimulus neuron firing rate greater than 0. So with this first validation of the correct input-output mapping, we are now focusing on the brain model. And to this end, we are moving away from Neurorobotic platform for now, and we are using the Brain Scaffold Builder. That is a Python package that enables spatially, topologically, and morphologically detailed simulation by allowing user to place neurons in a 3D space using 3D coordinates. So we started by reconstructing a microcircuit of the somatosensory cortex, a cortical column, according to the data collected from literature. So we placed the cells according to the layer dimension, the number of excitatory and inhibitory neurons, as well as their soma radius. We then started to examine the connectivity of these cells by using a Python script to automatically extract the connectivity data from the state-of-the-art of cortical microcircuit connectivity, that is the Markram rat somatosensory microcircuit. And we did so because the original Markram work uses 55 morphological types of neurons, while we only want to use 5 types of neurons. So 3 inhibitory neurons and 2 excitatory types of neurons. So we use the script to extract all the connection probabilities for each layer, for each morphological type, that we will use to connect the cells with a distance-dependent connectivity profile, as well as complex topographical shapes. With this approach, we are willing to reconstruct the microcircuits for also thalamic nuclei, and then we are going to use the cerebellar scaffold already developed and validated by University of Pavia. And in order to connect all of these different scaffold implementation at the mesoscale level, we are using the data-driven connectivity from the Allen Institute for Brain Science. In particular, we are using the mouse connectivity dataset to extract all of the information between the projection experiments between areas, so that we can not only validate the connection from literature that we found, but also investigate new connection that might have not been explored in these kind of experiments. And with this approach that I just described, we are planning to implement the whole scaffold and to compare its steady-state activity with experimental data, so that once there is coherence between the in vivo and in silico data, we can embed the scaffold with synaptic plasticity and functional mechanism, so that it is would be able to perform learning and training phase. And finally, we are planning to port the scaffold on the Neurobotics platform to perform the complete reach to grasp experiment with the ICAP humanoid robot. And with this, I thank you all for your attention. And if you have any question, I'll be glad to answer them.
Thanks a lot, Francesco. And we can now move to the second speaker, and then we will have the global discussion, merging all the questions at the end.
Sure.
We have Juan Pablo Romero Bermudez from KTH. Juan has a bachelor's in electronics and a master's in embedded systems and medical engineering. He currently works at the Neurocomputing System Lab at KTH under the supervision of Jörg Conrad. And in his talk today, he will show how brain-inspired control might be able to outperform conventional approaches in scenarios where dynamic, real-time human-robot interaction is required.
So I'm going to start by talking about cyberphysical systems and in particular robots. And I'm going to state two popular opinions, which are that the field of robotics is constantly amazing us with its advances and that progress still needs to be made so we can see robots more closely mimicking what humans do. I have chosen these videos to highlight this point. So here on the left, we have an amazing demonstration of what current robots can do in controlled environments with pre-programmed behaviors. And here on the right, we have the same robot during a live demo where at least two major things are noticeable. So a natural walking pattern without arms swinging and with flat feet and no extension of the leg, but most importantly, with a human remote controlling. So the question for me is, if the robot is capable of doing what we just saw on the left, why does he behave the way it does on the right? And part of the answer can be explained with the following, perhaps redundant statements. So yeah, conventional control techniques are fundamentally mathematical abstractions of the physical world, and behaviors are pre-programmed by geniuses that build equations to model reality within certain constraints. This, of course, is due to the fact that cyberphysical systems interact in real time with the environment where they are embedded. And this embeddedness implies high dimensionality, and real time adds constraints to the interpretation of the data. So basically what I'm saying is that conventional control methods can account for part of the embeddedness with decent latency. However, some elements are disregarded for simplicity or budget in terms of money or energy or footprint or other reasons. So this might sound daunting, but there is hope if we look at the problem from a brain-inspired perspective. Of course, currently it's not possible to simulate 100% of a human brain, but complex motor control can still be performed with more humble amounts of neurons, and advances in computing hardware are allowing researchers to simulate more intricate networks and incorporate reinforcement learning techniques into their methods. This is promising because in cyberphysical systems, physical and software components are deeply intertwined to be able to operate on different spatiotemporal scales, and agent behavior could emerge from physical interactions between body and world. At my lab, we want to explore these possibilities and hopefully provide robots with brains. Now, we want to focus on a paradigm that is that has not been thoroughly explored yet in this context, and this is the spiking neural networks. Now, spiking neural networks offer several advantages and are limited in some aspects. For instance, they model membrane dynamics, which require complex computations. They're event-driven, which allows asynchronicity, but their equations are not differentiable. They incorporate time dimensions, but require encoding and decoding of signals. They are inherently sparse in terms of activity. Hence, they can be low power, but they are not so popular yet. So there is not enough tools compared to ANNs. So these advantages are attractive, but can only be useful if the drawbacks that we see on the right are mitigated. The question is how? And one answer, an obvious answer maybe, could be by making use of the appropriate computing hardware. And I have chosen this picture here that I hope is self-explanatory to illustrate the problem. So let's think about ANNs and how reasonably well served they are today by CPUs and GPUs. But 20, 30 years ago, their value was not fully appreciated due to insufficient computing power. The same could be the case for the spiking counterparts. So spiking neural networks are poorly served by conventional architectures, but why if they weren't, right? Well, it might be the case that to make the spiking paradigm shine, different computing architectures are required. And that's why we use neuromorphic hardware. Our colleagues in Manchester have developed the Spinnaker Machine, a neuromorphic computing system, as you may all know. And we have 24 of these boards in our lab. In these 24 boards, we have about 20,000 cores with simulation and input-output capabilities. We can simulate roughly 20 million neurons, 20 billion synapses, and we can inject and extract event-based data at a rate of around 20 million events per second. And yeah, now that I have presented this which is our neuromorphic computing system, and the reason for us to have one, which is that, and I insist, run spiky neural networks in real time, I want to talk about how we use it. So I'm going to briefly present exploratory work that has allowed me to become familiar with the environment and prepare my future research. But first, I want to share my vision with you. So I believe that spiky neural networks can outperform conventional methods for real-time control of closed-loop systems. And I have justified hopes, namely that spiky neural networks are asynchronous and exhibit low latency when run on neuromorphic hardware, which leads to fast responses. They present sparse activity within their massive parallelism, which can lead to lowering energy budget, which of course can be useful for battery-operated devices. And they add a temporal dimension to the local computations by integrating membrane dynamics, which leads to compact representations. Now, from these hopes to the reality, there is a gap. And this gap can be closed by exploring, of course, related work and customizing it to our needs, and selecting appropriate tasks and scenarios where the potential benefits are highlighted. So one of these scenarios could be this one. Isn't this exciting? I mean, I know it's cute, but imagine a world where heavy-duty tasks and monotonous tasks can be accomplished by robots interacting with humans. Well, that is a collaborative scenario that I would like to witness one day, and I believe that my work can constitute a step towards that. Now, I'm going to show you a couple of projects that are part of my exploratory work. I'm going to start with this toy project in which we instantiated a simplified model of a cerebellar network that works as a controller for a two-joint Mayo robotic arm. A Mayo robotic arm, as opposed to a conventional robotic arm, is actuated by tendons instead of conventional actuators that mimic stretching and tightening of muscles like in humans. This approach is highly nonlinear and is very challenging for conventional control methods, and that's why we need self-adjusting controllers. We provide our cerebellar model, inspired by Eduardo Rosas, with a desired hard-coded trajectory from our pre-programmed motor cortex. The cerebellum produces a torque output that the arm interprets and upon which it acts. And finally, the proprioceptive information from the joints is fed back to the cerebellum, which tries to correct for any discrepancy. So in this project, we explored how proprioceptive information can be integrated with motor commands in real time. We do it in the NRP. We do it outside the NRP, like with our physical setup. And now in the following project, we currently explore how visual information can be integrated with motor commands in real time. We do that by using our robotic head to reproduce eye and neck movements when tracking an object with event-based cameras. Our robotic head has 6 degrees of freedom, 2 motors in the neck, 2 motors in each eye to produce rotation in 2 axes. This is sufficient to perform smooth pursuit and vergence for tracking depth. This is an ongoing project where we are using a network that mimics the behavior of the superior colliculus, starting from a retinotopic representation of the visual field. And currently, it behaves in a similar way a Breitenberg vehicle does, but we are setting plans for extending it with an attention module. Now, the projects that I just presented are exploratory work that makes sense in the bigger picture of the HBP. And in this context, we plan to leverage on research that has been done by some of our colleagues who work in large simulations of brain regions related to sensory motor integration. We are also in charge of making tangible things happen. That's why we're involved in different levels, like motion control, vision, and of course, physical systems. And the idea of this project is to integrate neural architectures with different levels of cognition by means of a demonstrator where a robotic arm and a human collaborate. We envision that not very far in the future, we might be able to see scenarios like this one, where an impaired person regains autonomy, or this one, where a robot helps a human with a monotonous task. But these scenarios cannot happen with conventional robots. And the reason for that is that they are not designed to interact with rather unpredictable agents, the humans, without representing danger. Conventional robots are precise and accurate, and they can be really strong, and that's why they are widely used. However, they require their own workspace where humans can't enter, and that's why we usually see them enclosed within restricted perimeters. Collaborative robots, on the other hand, are designed for human-robot interaction. They coexist and cooperate with humans. They are responsive. And the underlying difference between them and the conventional approaches or conventional robots is the way safety is achieved. So collaborative robots are compliant and they're capable of understanding scenes. This is achieved by providing them with proprioceptive sensors, especially torque, and vision with high temporal resolution. And this is exactly what we have in our lab. So yeah, this is our event-driven Corobotics setup. We have an open workspace accessible to humans. We have a 7-degree robotic arm with active compliance. The activity that takes place in the workspace is monitored by 3 event-based cameras. Event-based cameras only transmit information that occurs in pixels where light changes occur. And this makes them useful to track moving objects. And that's why in the video, you can only see the edges of the moving robot in the screen. The purpose of this setup is to experiment with different collaborative tasks, especially human to robot handovers. And this is because today that is a trivial task for humans, but robots are still very clumsy at that, as opposed to robot to human handovers, where the human is the source of the motor fluency. Of course, we are still not there yet, but we are taking the right steps towards it. Now, wrapping up, I motivated our research, namely that we want to embed artificial brains into cyberphysical systems. I talked about the advantages of spiking neural networks for scenarios where high dimensionality and real-time constraints are recurrent. I introduced neuromorphic computing platforms, ours especially, as tools to enhance spiking neural networks by mitigating their drawbacks. And I presented my vision together with the exploratory work undertaken under the umbrella of our academic collaboration with the Human Brain Project. Now, I want to just close this with an outlook to my plans. So currently I'm exploring different aspects related to reaching and grasping in the context of handovers. I'm trying to identify spots where neural approaches could show drastic performance improvements over conventional methods. The focus today is reactive trajectory planning, but this might involve attention and simultaneous localization mapping and obstacle avoidance. And with this appetizer, yeah, I would like to finish my talk, and I hope to come back rather soon and serve main dish and dessert. I'd like to thank the people at my lab, Jörg and Jens, Spinnaker team and Neurobotics platform team, and of course, Human Brain Project education team for this opportunity. And of course, thanks to you all.
Thanks a lot, Juan, for your super interesting overview of neurorobotics. So we can now start the discussion. We have 5-10 minutes to address the questions that have been coming in the Q&A. So the first one is for Francesco. Do you think it would be possible to run the same experiments in a physical environment rather than in simulation? What difficulties would you expect to see if you attempted this?
I think it would be possible. Also, Juan presented the tools that should be required and would be required for such in real life implementation. But I think the difficulties will be also the ones that he talked about, and specifically, well, in our specific scenario, there will also be some difficulties regarding for instance, multi-sensor integration of planning that would require distributed hardware, not only, let's say, the prototype that Juan is currently working on that need to be designed for a specific task, but also it's going to, it might need additional areas as well as a way to balance the whole robot movement, also because we are not in our, let's say, in-silico implementation, we weren't simulating complex movements, but in real life we would also have to account for weights and gravity, specifically for the robot to balance itself during the grasping movement. So there are certain degrees of freedom that the real life would get, that in silico can be, let's say, well, not avoided, but approximated easily. And also, a distributed architecture would probably require a real-time computing power that, again, might exceed also the existing one. I'm not very familiar with neuromorphic hardware, but the numerosity that we are planning to embed in the scaffold is quite large, and the Neurobotic platform allows to, let's say, slow down the frames of the physical simulator. So there is a message passing between the two simulators running in parallel that it is indeed real time, but with a increment of time between the two simulators that follows the software requirements. So the same thing in vivo, let's say, would require the real time is fixed. So the real time is the time passing in the real environment. And so there are these critical points that should be addressed.
Yeah, and thanks a lot. And I absolutely agree that can there be a lot of synergies between your works, and it's what is also ongoing in the HBP, this synergy between the in-silico and the real-time robotics world. We can then move to the next question, which is for Juan. You talked about complex motor control that can be achieved with reasonable number of neurons. Could you delve into this a bit further, please?
Yeah, so basically when I mentioned this, I was talking about one of the papers that inspired us for our first exploratory work. So in this paper from Eduardo Ross, basically they have an instantiation of a cerebellar model where they use around 64,000 neurons and they still achieve interesting motor control. And theoretically, given the hardware that we have, we can simulate up to 20 million neurons. So we might be able, being smart enough to put things together to simulate interesting complex motor behavior. And just to have an idea, the number of neurons that you have in a bat is around 30 million. So, and these bats, I mean, they can fly and they can land upside down and stuff like this. So, I mean, of course, we're dreaming a bit, but these are things that, in theory, could be achievable.
Yeah, and so related to this, from Pedro, we also have another question on the encoding. What kind of spike encoding do you think would work best for each part of the exploratory work? Would rate encoding work for both cases, or would precise spike timing be useful in that case?
So to be honest here, we have been using rate encoding. So in the second exploratory work, we basically just get information directly encoding as events because we use event-based cameras, right? Then the decoding for the motor control happens in rate encoding. For the other project, we used rate encoding. We didn't have much luck there, but also I think it was a matter of fine-tuning the model. It took us a while, and also the model that we had in the Neurorobotics platform didn't necessarily represent 100% reality. It was a bit far away. So, I mean, several reasons led to that particular project not to give a successful outcome. But yeah, so just to answer, we used rate encoding, but I think, of course, we should tackle other types of schemes.
Okay, and related to this, we have another question. Could we use spiking as a dropout?
I don't understand the question. As a dropout?
Maybe, Ankit, can you clarify a bit? And we can now move to the next question in the meanwhile, which is for Francesco. How do you expect the computational cost to change when importing the scaffold reconstruction to the NRP?
Well, what we did so far with the testing on the Neurorobotics platform was keeping the computational cost very low. So we used a very small scale spiking neural network. So, and these already proved to require a bit of computational hardware. So I surely expect to use supercomputers and dedicated hardware infrastructure to be able to perform the experiments with the Neurorobotics platform, with a scaffold on the Neurorobotics platform. But I know that the platform is already parallelizable, so it's already designed to run on these kind of infrastructure. So the only, let's say, open issue that we have to think about will be to port the scaffold model within the platform itself. But then the computational cost can be, let's say, faced with the proper hardware choice.
Okay, thanks, Francesco. And in the meanwhile, from Ankit, we have clarification of the question. Can we use controlled dropout probability of convolutional neural network as somewhat replication of spiking characteristics?
So yeah, I'm not familiar with this, so I cannot answer this question. I'm sorry.
Okay, and we have one last question for you, Juan, from Jens. You talked about Corobotics. Couldn't you extend this to autonomous robotic agents? Wouldn't this be obvious if neuromorphic hardware is so energy efficient?
Yeah, thanks, Jens, for the question. So I wouldn't say it's obvious. So right now we are using this big neurocomputing platform that is very bulky and it actually consumes a lot of power. And this is because, initially, the Spinnaker machine was designed to do large simulations, right? Right now we have been working with the Manchester team and they have tried to help us into creating ways to inject and extract events, but still the platform is let's say more general purpose than anything. Now we have hopes, and of course this is related to the project that they have now running, Spinnaker 2, where they basically take one of these big boards into one chip, and we at the lab are actually developing a standalone board that we want to actually embed in mobile agents. So I don't think it's obvious. I would say it might be possible, and actually people are doing it right now with Loihi and these more, let's say, small scale neuromorphic hardware platforms. But yeah, so I think it's not obvious at all. Yeah.
Thanks a lot, Juan and Francesco. I think we reached the end of our coffee break. So we thank again you and all the attendees for the fruitful also discussion. And just some small announcement. We will have a long summer break for Tea Slides. So the next session will be on the 7th of October, where we will have two talks by Ingrid Berke from the University of Oslo and Massimo Grillo from Politecnico di Milano. And of course, if you wish to present your HBP work in the future HBP Tea Slides, just send your application to Education Human Brain Project, and you could have the chance to share your work with your peers. So we really thank a lot, and hope to see you in the next HBP events and Tea Slides. Have a nice afternoon. Bye, everyone.
Bye bye.
Thank you. Bye. Bye.
Bye. Bye.